This is my code demo for my final project for ECM3423. As you can see, we have just loaded up the program and we are greeted by some menus which are handled by IMGUI. The buildings are lit using a directional light, a series of point lights and a series of spotlights. The directional light can be changed by presets, which will just change the direction and colour properties. They can also be manually edited here. The skybox can also be changed, so if I go and have a look at the skybox, I can change it to different values. A player spotlight can also be enabled, which can be seen here. There are also a bunch of different point lights in the scene. For example, this police car racing past has a point light attached to it that is changing colours, and my spotlight can be seen illuminating the scene as well as all these other multiple light sources. The environment map can be seen in action here, where currently only a static environment map is selected. We can change the environment map to dynamic, where it will dynamically calculate the environment map by re-rendering the scene 6 times in each direction from the object's point of view. You can also change the type of model that is used, so I can change it to a taxi, a car, a dinosaur, a sphere, which can be moved up, or a cube. Currently only a static environment map is used, which simply, instead of using the cube map created by the environment map, it uses the skybox in order to save on efficiency. The animations can be seen as follows by all of the moving cars, moving around the scene, and all of the animated flying police cars flying up and down the road. All of the objects in the game are texture mapped, meaning all of their textures are mapped to the object, and that can be seen here, as well as with all the buildings and the roads and the floors. All of the objects are also normal mapped, which simply gives the illusion of 3D geometry even though they are 2D, and it does this by changing the surface normals, which changes how the light reflects off them. The dinosaurs can be seen in the scene wreaking havoc on a London city, causing the police cars to be flying about. You can go to the different dinosaur swarms, all of the different cars, all of the police cars. As well as this, you can also bring traffic lights in. Bringing in traffic lights illustrates how many different light sources can be used in the scene at one time. For example, enabling the traffic lights. This brings an extra 20 point lights into the game, and you can also change the colour of the point lights. And this is better illustrated at night. From the scene settings and the sheer amount of data in this world, I'm using a technique called instance rendering in order to only have one single instance of the geometry and different matrices in order to define the different positions within the scene. This can be illustrated by the fact there are only 16 models, however there are very clearly much more geometry in that. So those models include the different cars, buildings, tanks, traffic lights, and floors. So there are only currently 16 draw calls within this program. In order to achieve functionality such as texture mapping, inside my scene setup function, which gets run on initialization, during the add floor method, for example, we can see that I define a material. A material simply represents the lighting properties as well as the texture maps. In this case, I'm specifying a texture map of a brick wall texture and a normal map of a brick wall normal texture. These textures can be seen here. When the model is created via this model from mesh class, which inherits from the base model class, when it is bound, it checks for the material maps. If they exist, it creates a texture from them. And creating a texture from them creates a texture buffer and then loads the image data onto the texture buffer. Once the material map is loaded, it will initialize the vertex buffers for the vertex attributes. The vertex attributes are defined by the mesh class, and the mesh class is passed in initialization. The mesh class simply stores all of the vertices, and the vertices include the positions, normals, texture coordinates, and so on, and the texture coordinates are used for texture mapping. You can see from when I create the floor, I simply load a square mesh, and the square mesh is simply a list of vertex positions, faces, and texture coordinates. These texture coordinates are used in texture mapping, 0, 0 representing the top left of the picture to sample, so in the brick wall example that would be here, and 1, 1 representing the bottom right, so that would be there. When the base model is created, the index buffer objects are initialized via this initVBO function, and this works by simply creating a vertex buffer, which generates a GPU buffer and passes the data onto the buffer. This data is then made available in the shader when the shader is bound to the model, and we can see this happening here. The shader class is represented by this base shader program class here. The base shader program simply takes a name which corresponds to a folder in the shader directory which contain vertex and fragment shaders. The shaders go through a pre-processing step which can be shown in the function here, and simply the include lines will be removed and replaced with the file they are referencing. For example, we can see the include directives here get replaced by the file util/material, and it dumps this code in place of the include line here. This avoids code repetition and makes development much easier. In order to make the texture accessible from within the shaders, when the shader is bound, it calls the bind texture method, which binds a specific texture to a specific shader texture unit, which lets the texture be accessible by this sampler name. This can be seen in the code here, where in the material class, a texture sampler with that name is used with the GSL texture function to sample the texture unit at that slot with the fragment texture coord. The fragment texture coord is passed through from the vertex shader. The vertex shader is run per vertex, and the fragment shader is run per pixel, and the texture coord is interpolated between the pixels. This is how the texture mapping is achieved. Specific instances of the base model class can be created, such as the instance model, which inherits from base model, and all it does is, instead of using GLDrawArrays, it uses GLDrawArrays instance, with the number of instances it should render specified. As well as this, specific model loading functionalities have been added to the base model class, as well as the comp model, which allows models that are made up of multiple meshes to all have the same parent transform, which can be seen here in the draw method, which uses a transform passed in and multiplies that transform by its own transform. The transform class defines the model matrices and simply contains functions to manipulate a transformation matrix using the GLM library. The transform class is what is used to animate the scene, as can be seen in the add cars method. The car instance class is created, which inherits from one of the base model classes. This explicitly defines a shader, and this shader is used to draw the model using the Phong lighting model and instance rendering. It also passes in matrices to define the position of each instance of the geometry. The add car method specifies a list of grid positions to linearly interpolate between during each update. As can be seen here in the update method, the grid positions are interpolated using the linear interpolation, which simply involves getting the current grid position of that instance and the next grid position of that instance, converting them to world space using my coordinate system class, which simply just multiplies them by the separation. The linear interpolation equation is then applied, which simply just calculates the difference vector d and calculates a percentage of that using the linear interpolation factor, which is updated each frame. The angle between the d vector is then calculated. The matrice for that specific instance is then rotated and then translated after. The order is important because it rotates about the origin and then translates it away from the origin afterwards. This specific class uses the Phong shader normal map instance matrices shader. This simply takes in a big uniform list of matrices and then differentiates between the different matrices using the instance ID. The matrix is then combined, calculated the position in normalized device coordinates, forwarding on the fragment shader, and in order to do normal mapping, the TBN matrix is calculated using the utility function TBN calc TBN, which simply converts the tangent space normals into world space. This is how animations are applied to the scene. In order to do environment mapping, a cube map is created, and a cube map is a specific instance of a OpenGL texture, which simply stores a texture for each face of a cube, or more for each 6 faces of a cube. The environment map simply generates a bunch of frame buffers, which can be used to render the scene off-screen. 1 frame buffer is created for each direction in the cube map. These frame buffers are then bound to textures, and also they are added a depth buffer too. This depth buffer is important because if it's not added, then the scenes will not have a sense of depth, and different objects can be incorrectly placed over each other. When the depth map gets updated, it calculates the different camera views. This is done by using the GLM lookup function to calculate a view matrix at the object position and in the specific directions. And these directions are relative to the cube map faces. and it essentially loops over each of the frame buffers, binds the frame buffer and clears it, sets the camera to the calculated view using the calculate camera views function. It draws the scene's reflections, which if we look essentially just loops through the models and draws them, unbinds and then repeats for each face, and then all of the camera vectors are restored afterwards. This environment map is used by an environment shader and is simply sampled in the environment shader, which can be shown here. We can see the sampling happening here. So first the reflection is calculated, the reflected ray along the normal, and it is sampled using the texture method and the env map, which is the uniform sampler cube. It's sampler cube instead of sampler 2D because it's a cube map, not a 2D texture. And as we can see, the uniform name is env-map, which corresponds to the env-map uniform, which is bound using the self.map texture. The last required feature that I've implemented is illumination. Illumination is done in the light class, the light file, which basically stores 3 different light casters. So the light source, which is a point light, a directional light, which just has a direction and colours, and then a spotlight, which has a cutoff angle and is the same as a point light, except for the cutoff angle. These light values are bound whenever the Phong shader model is used, as can be seen here. The light uniforms are created, and then the light uniform values are bound every time the shader is bound, and this is done using the scene's directional lights, all of the different scene point lights, and all of the different scene spotlights. And as you can see, for each of the lights, it binds the uniform list, and then all of the Phong lighting calculations are in a utility function so that they can be reused. The directional lighting calculations are done using the lighting equation. So it calculates the diffuse component, the specular component, and the ambient component, and then multiplies them by the material's properties and the light properties, then returns the combined values. It does this for point lights, spotlights. Point lights simply add the attenuation factor. Spotlights add the attenuation and the cutoff values. These functions are used in all of the Phong shader pairs, so that can be seen here in the include line, and then the final color is calculated by applying the directional light, which is received as a directional light uniform, which is stored here inside of the lights.gsll file, which just stores the light structs. So back to the shader, we can see that the final color is calculated by the directional light, loops through all of the point lights, and calculates the point light contribution, and the same for the spotlight, and then combines the final color here, which is a combination of all of the different attenuations from all of the different lights. The last thing I'd like to discuss is how the city is generated. So the city is generated using a city map, and essentially this is just done by calculating a big map where zeros represent roads, -1s represent a horizontal road, and then anything above 0 is a building. These buildings are then created in the generate city class, where an instance Phong shader, which is the specific normal map one, is used for the roads in order to save computation times and use less draw calls. It then loops through the city map and then adds position offsets to the road shader, so that they can be used to calculate the final position of the building for each specific instance. This is done for the roads, the vertical and horizontal roads. They're done in separate draw calls, and the buildings. So the buildings are simply generated by a building pack, which is simply in the models building pack, and all the different building folders are in here. A single instance of that building is created, and which can be seen inside the generate buildings method here, where a single instance is created of this towers class, and then when the city map is created, it's using the towers add tower method, which adds a offset uniform, which is applied in the Phong instance normal map shader. The Phong instance normal map shader can be seen here, where the offsets are received as a uniform, and the specific offset is retrieved using the instance ID. The offset matrix is then calculated and then combined with the model matrix, and the final normalized device coordinate is calculated using the position view model matrix with the offset. The combined matrix is used to calculate the world space TBN matrix. The program uses a combination of OpenGL tricks and techniques in order to generate a finished final scene which is efficient and has lots of geometry, using animation, texture mapping, normal mapping, lighting and illumination, environment mapping, and instance rendering.